This is paper 3 from 2016, and just about every paper 3 is going to have a Maclaurin series on it. So this first problem is about a Maclaurin series. We're given a function, and they want you to find the Maclaurin series out to the x cubed term. Well, if you remember, and it is in your formula packet how that works, how it expands, the Maclaurin series will be the function times x to the 0 over 0 factorial, and that pattern continues. Then the first derivative, x to the first over 1 factorial. Notice how those numbers match. Second derivative, 2 derivative, x to the 2 over 2 factorial, etc. So the last one we need for this problem is the third derivative of x, f of x, times x cubed over 3 factorial. So the rest is just figuring out those derivatives and evaluating them. Well, f of x, well, f of 0, let's just create a little list here. F of 0, if you sub in 0 into that function, you get e to the 0, which is 1, and the sine of 0 is 0. So that is going to equal 0. So now we need the first derivative. So we take the derivative, product rule first, e to the x, derivative of the second, cosine x, plus second e to the x, and then sine x. All right, subbing in 0 there, so f prime of 0 is e to the 0, which is always 1. We can kind of ignore those e to the x's. Those are always 1s. So we got the cosine of 0, which is 1, plus the sine of 0, which is 0. So that's going to equal 1. Second derivative? I think what I do here probably is factor out the e to the x before taking out the second, or taking the second derivative. So let me do that up here. E to the x times cosine x plus sine x. I think that might be a little easier to deal with. And then we can use the product rule between e to the x and the parentheses. So here goes. Product rule. First, e to the x, derivative of the second. What's in the parentheses? Derivative of cosine, negative sine. Sine is cosine. Okay, middle of the product rule. First, derivative of the second plus second, cosine x, sine x. Plus sine x. Let me stick that little plus in there. Okay. Times derivative of the first, e to the x, and there we go. Okay, should we clean that up? Nah. Or should we just go ahead and sub in 0? It doesn't matter. We'll sub in 0 and see what happens. So, again, e to the x, that's always going to be 0. So we have negative sine of 0. That's 0. Cosine of 0 is 1. Cosine of 0 is 1 again, and sine of 0 is 0. So that adds up to a big fat 2. So f double prime is 2, f prime was 1, and we got one more to go. F triple. All right, this is going to be a little messy. Maybe I should go back up and clean this one up before we try that. So I notice I have an e to the x negative sine x and e to the x positive sine x. That's going to cancel. And then I've got e to the x times cosine twice, so that's 2 e to the x cosine x. That's the second derivative cleaned up, which is going to be a lot easier to work with than taking the third derivative. So the third derivative, here goes, product rule one last time. First, 2 e to the x times derivative of the second, negative sine, plus second cos x. Derivative first, 2 e to the x. All right, subbing in 0 one last time. So we got 2 e to the 0. That's 2 times 0 for the sine is 0. Cos is 0, 1 times 2 equals another big fat 2. All right, we're ready to do our Maclaurin. Let me scroll up just a little bit more so I can still see it. There we go. So f of 0 was 0. So the first term turns out to be 0. That was this part of it. And now f prime is 1 times x to the 1 over 1 factorial. That's done. F double prime at 0 was 2 times x squared over 2 factorial, which is 2. And then our x cubed term is going to be f triple prime, which is 2x to the third over 3 factorial. 3 factorial, 3, 2, 1 is 6. And there's our answer. Let me clean this up a little bit. Final result, x to the first plus x squared plus x cubed over 3. Okay, there's our Maclaurin series. Now let's see what we have to do next to that. It was all, let's see, how many marks was that? That was 7 marks. Okay, so for part B, they want you to evaluate a limit. Now it says hence or otherwise. Hence means using the previous result from part A. Otherwise means don't. Do it any way you want. So I'm not going to really worry about part A. I'm just going to jump into this and see what happens. I'll evaluate the limit as x approaches 0. So I get e to the 0 sine of 0 and see what this is going to equal. Minus 0, all over 0. Well, the sine of 0 is 0, so what we get is 0 over 0, so this qualifies. Since it's an indeterminate form, it is a L'Hopital case, 0 over 0. So I'm going to use L'Hopital on it by taking the derivative of the numerator and denominator respectively and trying to reevaluate. So the derivative of the numerator, e to the sine x, well, I think I had done that earlier in part 1. Yeah, its derivative, looking back, was e to the x cos x. So I guess I'm using the hence part here. I'm using the previous part's work. E to the x sine x. Okay, so I've taken the derivative of that section. Minus x, so minus 1, and then minus 2x, all over 3x squared. All right, now evaluating the limit as x approaches 0, I get e to the 0 times, so that's cosine 0 is 1, so 1 plus 0 minus 1 minus 2 times 0 all over 3 times 0, and 0 over 0 again. Well, if there is such a term, I'm going to re-L'Hopital it. So here we go, one more time. Okay, derivative again. Oh my gosh, it's getting messy. But did not I do this before? Yeah, so hence, let me look back and see what that derivative was. Because that's the first derivative, what I just circled, and the second derivative I had done in the Maclaurin series. And the second derivative boiled down to 2 e to the x cos x, using that previous work. Minus 1, the derivative of that goes away, and then minus 2. X becomes minus 2 over 6x. Evaluating at 0, 2 times 1 minus 2. Oh gosh, I can see it. Over 6 times 0, 2 minus 2. Yeah, one more time. Should do it. I'm guessing one more time because I look at that denominator and that's going to become a 6. So I'm going to re-L'Hopital this. Limit as x approaches 0, and yeah, hence I'd already done this one before too, so let me look back. That turned out to be negative 2 e to the x sine x plus 2 e to the x cos x, and the 2 goes away when I take its derivative. Bottom becomes a 6. Please be something other than 0 over 0, which I think it's going to. So plugging in a 0, I get negative 2 times the sine of 0 is 0, plus 2 times 1. Oh, good. A 2 on the top, a 6 on the bottom, equals 1/3. There's our limit. So what do they give us for all that work? 3 measly marks. We'll take them. 2 parts done to problem 1, and 1 to go. All right, part C involves the Lagrange error. So Lagrange error form is in your formula packet, but let me refresh you on what that means. Remember, when you use the Maclaurin series, it's not exact. It's an approximation for a function as far as what it's going to equal, and the closer or the further out you go on the number of derivatives, the closer it's going to be. But there's always a slight error, and to find that error, all you do is, we stopped at the third derivative when we did our Maclaurin series. So the error is equal to the fourth derivative evaluated at some c, and I'll explain that in a minute, times x to the fourth over 4 factorial. Again, those numbers match. Fourth derivative, x to the fourth, 4 factorial. Now, the fourth derivative we'll need, so we can figure, well, I got to go back and look at the third derivative, which was negative 2 e to the x sine x plus 2 e to the x cosine x. And I didn't clean that up at all, but I will now. I'm going to factor out the, I'll factor out the negative 2 e to the x. And that'll leave us with a negative sine x, and then factor out a negative 2. No, I'm sorry, that'll leave us positive sine x, and then negative cosine x. Okay, so I'm going to take the derivative of this using the product rule. All right, here goes. Fourth derivative. So first, negative 2 e to the x. Derivative of the second is going to be cos. Derivative of sine is cosine. Derivative of cosine is negative sine. So that's plus sine x. And then plus the second, which is sine x minus cosine x. Derivative of the first is negative 2 e to the x. Now, this is paper 3, calculator friendly, because it's going to get just a little bit messy, but you can use your calculator. So there's your fourth derivative. Then you evaluate that fourth derivative at the largest value, the value that's going to give you the largest error. So in other words, between what we centered our series around, since it's Maclaurin, it was centered at 0, and we're trying to evaluate it at 0.5. So between 0 and 0.5, which number in that range of numbers is going to give you the largest error using that fourth derivative. Now, how do you figure that out? Well, what you could do, actually, you could graph the fourth derivative and see where the largest error is between 0 and 5. Or kind of think about this. Since the function, so the original function was e to the x sine x, and that is that's an increasing function, and you could graph that too and see that it's always increasing. Therefore, the values are getting bigger as you move to the right. So your largest error is going to be furthest right, which is 0.5. So the error is going to be the fourth derivative evaluated at 0.5, which is the highest point, times x to the fourth, which is 0.5 to the fourth, over 4 factorial. Now here's where the calculator really comes in handy, because you'll just have to sub in 0.5 for your x's into the fourth derivative, and then multiply times 5 to the 0.5 to the fourth over 4 factorial. And I have done that, and I got, and by the way, sorry, the Lagrange error is the absolute value. So this is, it turns out negative, I think. So it's negative 0.0823, 0.0823. So the Lagrange error, absolute value of the error, is 0.00823. And that's the answer to part 1. Now part 2, a little easier really. It says deduce from that error whether approximation will be greater than or less than the actual value. So you have a function, its actual value, we don't know. We're using the series to determine approximation, and we know that the maximum error for the approximation is only 0.00823. So is that greater than or less than the actual value? Well, since the error was negative, the error is negative, which means that the error is less than the actual value. And that's what you can just write that in words, that the error is negative, which means that the approximation is less than the actual value. There's the answer, which I won't write out. Let me say that one more time. Since the error is negative, that means that the approximation is less than the actual value. So the way they split this up, I'm sure that's only worth 1 there. The Lagrange is probably worth 6 because it was a total of 7. I haven't looked at the mark schemes, but that's just a guess. It could be 5 and 2. But that really doesn't matter at this point. Just be sure you know how to do Lagrange error. As I said, in your formula packet, the figuring out of part of the C where the maximum error is going to occur, that's the trickiest part. But as I said, you can look at that graphically to help you figure that out. And that's all of problem number 1. This test that year started off, that's a little harder problem. I think problem 2 is probably going to be a little easier. We'll take a look at that next.